Okay, so my work is about cybersecurity in interconnected critical national infrastructure. So I am a lecturer in Bristol Cybersecurity Group in computer science. Okay, let's go to the talk. In general, these critical infrastructures are cyber physical systems in different domains, such as power grid, factory automation, water, and manufacturing. And so these systems are combination of physical process and computation and communication. So if you look at it as a state transformation diagram, so we have a physical process across different infrastructures, whether it is water, power, or manufacturing, even robot. And the state of the physical process collected by sensors, and this information sent to the controller through a communication channel. And controller is nothing but a computer, like it's an embedded computer. We call it as a PLC, programmable logic controller. So based on the control logic, this controller computes the action for the actuators and sent through another communication channel. And actuators eventually change the physical process. So you can consider actuators in case of water treatment plant, water plant. Actuators can be water pumps or valve, which decides the direction of the water, and so on. So this is a state transformation diagram, how CPS works in general. And these systems are modernizing every day. Like last a couple of years, automation is increased in these systems, and many technologies, including remote access and communication technologies, increased for easy maintenance. So this leads many vulnerabilities from the cybersecurity aspects. And because of the safety critical systems, safety critical aspects, these are great target for attackers. For example, so there are very many well-known incidents. One of the earliest incident happened in 2000. So where one of the employee controlled the sewage water into the streets. You can see the picture right side, like it's a sewage water, and it came to know after a month, because in early 2000, so not many incident happening in this domain from the cyber security point of view. People never thought that it can be a cyber attack, but it was a cyber attack. Then similarly, one of the famous attack on nuclear plant, Stuxnet attack, where attackers destroyed some of the centrifuges in the nuclear plant. So this picture is from the nuclear plant after the incident. And similarly, so recently, like Ukraine power blackout, where attackers able to cut down the power supply for the customers, and same time they are also able to cut down the helplines. And similarly, Florida water plant attack. So recently in 2021, where attackers able to change the chemical properties in the water distribution system into 10 folds. Okay, so there are many incidents happening in this domain. And I want to show how the architecture of the critical infrastructure looks like, and how anomaly can birth and travel to the physical space, because majority of the cybersecurity in IT domain. So I want to show how the attacker can enter from IT domain and enter into a physical process and reach the attacker goal. Okay, if you see, if you can consider it is a distributed system. In general, critical water distribution system in a city scale or power distribution system in a city scale is a distributed system. So there are multiple sensors and actuators across the city, and these will talk to controller. Like each controller control a part of the system, and these controllers also communicate among themselves to have a bigger picture across the cities. And there are SCADA systems as well as historian. So SCADA is nothing but a supervisory control and data acquisition. So you see all the physical process states in a bigger screen. And historian is a database which stores the data every time instant. And there exist management systems which monitor the SCADA system and historian and so on. Of course, whenever management systems communicate with the SCADA systems or internal critical infrastructure network, then they communicate, and there is a firewall which is able to detect whether it's an intruder or not. These are the different levels of the network. Level 0, which is close to the physical process, which is close to sensors and actuators, and which is level 1 is among different controllers. And there is another network close to the SCADA systems and so on. And so there exists attacker. Let's say assume that if the attacker is able to compromise or access some of these components within this network, either sensors, actuators, or controllers, or communication channels, or SCADA system. So when attacker able to access SCADA, so it is possible for attacker to send malicious commands from SCADA, such as, in case of water plant, opening the valve or closing the valve. In case of power plant, attacker can send command like, on the generator or off the generator, or open the circuit breaker and so on. And it is possible attacker can access communication channels as well as controller. This controller is an embedded device which has a firmware as well as software applications. So attacker can also access to that. So if the attacker is able to access close to the physical process, like level 0, so attacker can damage more from the physical process side. Okay. So I will show you how attacker can enter. So when attacker is entering into the system, if the intrusion is not detected, obviously sometimes the firewalls cannot detect all the intruders. So attacker can upload code which is going to the controller. For example, so we are controlling a motorized valve which can fill the tank in the water system, and attacker can change to open or close, or attacker can change the state of the sensors. And similarly, attacker can change the actuators commands. And when eventually these commands will reach to controller, and controller is also compromised and safety conditions are not able to detect it, it will reach the actuator. So actuator will cause the impact on the physical process. So that entire physical system move to the unsafe state. Eventually the physical process will be affected and it will move to the unsafe state. So as you know, every system is connected. If there is a anomaly or unsafe state, the impact of it move to the another stages. For example, if you consider this as a first stage and this as a second stage, so if there is an anomaly in the first stage, eventually the physical process is connected, so this will impact the other parts of the system. So majority of my work is in the context of SWOT test bed, so where we have 6-stage distributed control system. This is a real operational plant in a room scale, where we have 6 distributed controllers which control 5 gallons of water, which produces 5 gallons of water every minute, which has a number of sensors and actuators and multiple filtration systems with wired and wireless communication channels. Okay, I'm not going in detail. This is a simplified view to represent all the 6 stages, where we have multiple sensors and actuators, such as you can see, like MV is a pump, motorized valve, and P is a pump, and so on. There are multiple PLCs. Okay, so I want to show you a simple example by compromising only one component. It is a single point attack where attacker is at level 0 and attacker intention is to overflow the tank 101. Okay, so you see this is picked up from the same plant which I showed, the SWOT. So you see, like, there is a motorized valve. Whenever this motorized valve opens, so water comes to this tank. The tank is T101, but the level of the tank is measured by LIT101. So there is a PLC, nothing but a controller, controlling the level of the tank. The controller responsibility is to open or close the motorized valve to maintain the water level. And similarly, there is a pump, water pump, which sends the water from one place to another place, depends on the requirement of the other parts of the system. Okay, so assume this is a time -1. When prior to the attack, the motorized valve is closed and the pump is on. Assume like green is on. Okay, so later attacker A6 comes into the picture. So here attacker name is A6, and attacker tries to open the motorized valve. So there are ways how to communicate with the PLCs or how to change the physical process state. So attacker can open the motorized valve and show the status of the motorized valve to the controller as closed. So controller cannot see the original status. It's kind of masking the original status. So eventually what will happen? Water will come into the tank and it will overflow. So now water is already filled and it is overflowing. So we conducted this experiment in the real test bed on a room scale. So this was the incident when it happened. You might think that, so okay, water is overflowing, so what's the problem? So assume the same attack is happening on nuclear plant, or similar attack is happening on power systems and so on. So is also interconnected, right? So for example, treatment system, when after producing the water, it will supply to the distribution across the city, and these two systems receive the power supply from a power source. Actually, these three are interconnected test beds are located at Singapore, uh, if where I was working before moving to Bristol. So if there is a attack on power system, and eventually this will lead to the water system. If there is attack on water treatment, the impact will lead to the water distribution system. There are cascading effects across different systems. Apart from different systems, even within the system, the system is not small. If you take a power system, it's a lot of stages. So if there is a attack on one stage, the impact will be on other stages also. So the screen you are seeing here, this is the SCADA system to see the power system on the big screen. Okay. Okay. So these are three different systems or which are interconnected. So in real life also we have a hospital and where we need a power source all the time. If there is an attack on power supply and power distribution, so the impact will be on hospitals as well, right? So these are interconnected systems. Okay. So in security in CPS, in general, this is not only about keeping attackers out, because eventually some way attacker is able to enter into the system. That's what we know from last many years. And how understanding the risks, what if attacker is in the system, and how we can detect an attacker, and how to mitigate and responding to adversaries that have partial access to your system. So these are the different ways how people view the security in CPS. So my baby steps towards, like, I was working initially creating attacker and attacker models, how we can understand and create attacks on these systems. And the second is understanding impact of the attacks and how to respond to these attacks. And third one is can we detect these attacks and how accurately we are able to detect these attacks. And third one, like, so after detecting the cyber attacks on the system, water or power system, how to respond to these attacks. So these are the different steps I was following for last couple of years. Okay, so I'm going to show one work which is related to the detection of anomalies. So we call it as DAD, distributed attack detection. So as you saw the example of overflowing the tank, so we want to monitor the physics of the system from the entire system and see whether we are able to monitor and raise alerts when the system is moving from safe state to unsafe state. So that is the underlying idea of this work. So we want to capture the safe states, and whenever the system is deviates from safe state to unsafe state, so we want to raise an anomaly. So I'm going to show only the brief of the idea. So okay, so this is an interconnection of first three stages in the SWOT, which I shown the picture, the room scale water treatment plant. So if you see motorized valve, whenever motorized valve is open, water comes to this tank, and there is a flow meter which measures the flow rate. And similarly, there are multiple other sensors like flow meter next to the pump, and there is a motorized valve which can open or close to control the flow of the water pump, and so on. Okay. Okay. So let's go to the. So what we are doing is we are capturing the invariants across the system. So these invariants captures the relationship across different sensors and actuators in the entire system, and we call these as invariants. There are different types of invariants, like state dependent invariants. So for example, whenever motorized valve opens in the previous figure, like the flow should be there in the pipe, the flow meter should measure the flow. If there is no flow but the motorized valve is open, that means there is the physics is not matching. And similarly, so whenever water level in the tank level, this is a level sensor, water level in the tank is low, and the input should be open, like motorized valve should be open. Similarly, whenever water level is high, the water should close, the mod inflow should be closed, and so on. So these are the different constraints of across the system. But similarly, if it is a continuous variable, for example, you consider level sensor. Level sensor is a continuous, so you cannot say like it's low or high. Sometimes it's a if the water level is from 0 to 1000 mm, so it's a continuous variable. So we are using state estimation to measure the continuous variable all the time. For example, okay, if you see, this is x hat of 0 is the estimation. We are estimating at 0th time. Initially we assign the previous value, but next time when we update the estimation, we use the previous value plus input minus output. What is the input flow and what is the output flow? So over a period of time, we are able to measure the difference between estimation and the real values for n number of values. So we calculate the average of these n values and decide if the average is greater than epsilon, we say there is a fault or cyber attack in the system. Otherwise, it's normal. So this is a state estimation in control systems. We estimate the state of the continuous variable over a period of time. Okay, so we consider these two invariances, state dependent and state agnostic invariance. So how do we derive these? So we derive these from the plant design. So we take the input of the CAD software where water plant is designed or any other critical infrastructure is designed, and what is the control code. We parse the control code and retrieve the conditions and derive the invariants using our approach, and we use them as a monitor. So whenever system reaches to unsafe state, so these monitors raise an alert. So this is for full approach, like please refer to the paper. And in general, these invariants act as a checkers. So whenever system move to the unsafe state, it raises an alert. Okay. So apart from testing ourselves with the approach, so we also participated at international live fire exercise defense. So where this entire water system is exposed to different attackers across industry as well as academia. And so I was participating as one of the defender from academia and to protect this water system. So I started participated from 2016 to 2021. Actually, I'm showing results from early results. I don't have slides for the recent results. So the attacker goals for the industry teams as well as academic teams, such as like closing or opening the motorized valve, or increasing the chemical properties in the water, or increasing the tank level in the water, and so on. So there are multiple attack teams participated. So if you see in 2016, if you see in 2016, so there are three industry teams participated as attackers, and similarly 3 academic teams participated. The same like in 2017, also many industry and academic teams participated as attackers and defenders. So this is a live fire exercise event, similar to a NATO event. NATO also organizes recently after looking at this event. So we also participated there to detect the attacks across all the NATO countries. So in 2017, these results are from 2017. So we are able to detect, if you see the total, we are able to detect majority of the attacks compared to 2 industry teams. The last 2 are industry teams. So these attacks mainly where process is moving to unsafe state, and we are able to detect that unsafe states thoroughly. Okay, so the previous work is about anomaly detection or attack detection whenever the system is moving to the unsafe state. This work, the second one, is model-based analysis and how we can generate a cyber attacks automatically. So for example, you saw the example scenario, how to overflow the tank. So how we overflow based on the system knowledge. And if attacker is able to learn how the system is connected, he can eventually he can perform an attack to open the motorized valve so that eventually water tank can overflow. So what about, we want to capture this entire information in the form of a system model. And we captured using ALI. ALI is a formal model, formal language. And whenever we specify a attack specification, so we are able to generate automatically the attack scenario. For example, if attacker wants to do overflow, so we can generate a scenario for overflow. If attacker wants to do underflow, we can generate a scenario for underflow. Even attacker wants to stop the water pump, which supply water from one stage to another stage. So we can stop by creating an attack specification. And eventually we are able to test on the real test bed and validated whether the generated attack scenario is accurate or not. Okay, so how do we do? So we automatically synthesize these attacks using formal approaches. So a system is said to be unsafe state whenever it is moving from safe state to unsafe state. So the goal of our analysis is to check there exists a system trace that results in an unsafe state. So here the system trace means what are the different actions attacker can perform in order to reach the goal. There are sometimes it's one, or sometimes there are multiple actions attacker needs to perform. So the model can generate multiple steps for an attacker. And similarly, we can also generate minimal number of steps or minimal number of components attacker can attack to reach a particular goal. Okay. And a same system we used. So we modeled the initial stages of the system in the formal language, and we are able to generate this trace. So Ally is a discrete language. So we are able to model the water system in the discrete way. So for example, if you see, so there are different ticks, different time instants. So in the time 0, the water level is L. L is low, and the reading is also L. So whereas the motorized valve status is off, it's closed, and its reading also closed. So whenever the reading is different from the state, that means there is an attack. So there is no, if you see here, so water level is H, but the reading is L. That means whenever the sensor is sending to the controller, so it is manipulated, and the manipulated value goes to the controller as L. Okay. So same time, so attacker is also masking the motorized valve, and motorized valve is continuously closed, but the original status is open. So eventually water is overflowed, same way as I explained in the previous slide. So we validated this by converting all the discrete values into continuous values. So there is a manual process involved to validate on the real test bed, but so we are trying to improve it with the continuous models at the moment. Okay, so the overview of my research, understanding what are the different vulnerabilities in the systems and how we can perform different malicious attacks, and how we can detect accurately using different techniques, whether it is basic cybersecurity techniques or machine learning techniques, and how we can mitigate these attacks and other safety and security assurances under cyber attacks. Okay. So there are a couple of ongoing projects at Bristol where I am involved. So we are looking at cascading effects of cyber attacks on interconnected systems. So as you know, water systems receive the power source, and if there is a attack on power, so there will be impact on water system. So we are studying cascading effects at different levels, like network level, physical level, and application level. And similarly, host forensics, once attack is detected, so how to find the root cause and where to look at the root cause. And this is still in the preliminary stage, even in entire academia. And the third one is automated incident response. How to respond when the system is in unsafe state. And at the moment, operators or who are working in the industry, they are doing manually. So we are trying to come up with an automated incident response so that it can help the operators. And similarly, we apply machine learning algorithms in this scope as well as formal methods. Okay. And in Bristol Cybersecurity Group, we have different infrastructures such as water system and building management systems. We have a SOC, which is a SCADA system, and many PLCs, reconfigurable PLCs, to play around in this scope and to work and improve the cybersecurity in national critical infrastructure. Okay. Thank you very much.